Just give me, I'll take the pointer. Okay, thank you for giving me an opportunity to speak on the advances in metal oxides and mixed metal oxide catalysis and their application. The content of my talk will be what is catalysis, how does catalyst work, why the metal oxides are used as in catalysis, how to synthesize metal oxides, application of metal oxide, what are mixed metal oxides, how to synthesize mixed metal oxide, application of mixed metal oxide, research opportunity and acknowledgement. The term catalysis was coined by John Jacobs Berzelius in 1835. The catalyst is a substance that increases the rate of reaction at which the chemical system approaches equilibrium without being substantially consumed in the process. The reaction, how does the catalyst work? From the reactor, it's an uncatalyzed way reaction. The energy required is very high and it comes to the products. When we have the catalyst, the energy required is very low and we are able to get the products. This is a schematic diagram, what we can see. Two reactants, they combine on the basis of the catalyst and the catalyst, then the reaction happens, the product forms, and the separation happens over here and the product comes out, and again the catalyst can be recycled. There are three key aspects of the catalyst action. A catalyst does not take part in reaction. It will change itself during the process by interacting with reactants or products. Will alter the rates of reaction. In most of the cases, the rate of reactions are increased by the action of catalyst. However, in some cases, the rates of undesired reactions are selectively suppressed. After reaction cycles, a catalyst is reborn. In practice, a catalyst has a lifespan. It deactivates gradually. Why metal oxides used as a catalyst? Because metal oxides are the most important and widely employed categories of a solid acid catalyst, either as an active phases or as in support. They can be used as in support or maybe a phase. Their acid base and the redox properties make them largest family of catalysts in heterogeneous catalysis. Since the symmetry and the coordination of the metal ions is lost at the surface, they show a strong tendency to become saturated by reacting with the gas molecules. In fact, in the hydroxylation reaction, if you can see, the result are two chemical reactions between the surface of metal and oxygen bond and water molecule. The resulting OH group densities are governed by a nature of the metal oxide. The metal oxides become a good catalyst because of the presence of surface acidity and basicity, presence of cationic and anionic vacancies, ability of cations to undergo oxidation and reduction, high mobility of lattice oxygen, interactions with light, photo-assisted surface chemical processes. The synthesis is taken care by these three methods: co-precipitation, Sol-Gel, and hydrothermal method. Just an outline of that. The metal nitrate has been taken along with the sodium carbonate, and then through the process we get finally a metal oxide as a nanoparticle, or the metal oxide as a catalyst. Sol-Gel method, we have got a metal nitrate, ethylene glycol, and acetic acid. When we combine that one, then we heat for 80 degrees centigrade, so then 140 degrees centigrade, and finally we are able to get the metal oxide as a catalyst. Like this, we have got a hydrothermal method with the precursors are used, and there is a various form. Suppose we want to dope that one with triethylamine or succinic anhydride or PEG acetic acid, so we can have that one on the cover over there. So we have got a metal oxide prepared by the hydrothermal method. This is an application of the metal oxide as a catalyst. We have got this diphenyl methane, which is reacting with the tertiary butyl hydrogen peroxide, MnO2 as a catalyst. The MnO2 catalyst has been prepared by calcination of the manganese nitrate and also by the reduction of the potassium permanganate. The manganese dioxide, which is prepared by the potassium permanganate reduction, was found to be a nano size and amorphous in nature. That's why the AnMnO2, amorphous nanosized manganese dioxide, has been written over here. And then the metal oxide and 20% conversion time required for 20% conversion has been calculated, and we found that the amorphous AnMnO2 requires only 2 minutes to get converted into 20% the product, and the initial rate has been calculated on the basis of that. So the reaction is here, TBHP. We have found that the 3 millimole of the TBHP is required to convert the product to 92%. Similarly, when we have studied the part of the conversions, is 92% conversion, we are able to get the ANMNO2, and the surface area of ANMNO2 is found to be 192.14 meters square per gram. This is a catalyzed oxidation for the various aryl alkyl arenes, and here we are able to say the 100% conversion also has been achieved at some of the cases. So 85 to 100% conversion has been achieved, and the selectivity is also found to be between 80 to 100%. The reactant when the product when it forms a 92% conversion is happening in the 2C case, it happens that the 1 millimole of 2,6-bis 1,1-dimethyl ethyl 4-methylphenol acts as a radical scavenger. That's why we are not able to get the product over here. And this work I have taken from one of my colleagues, is Anand Borangi. His work I have presented over here. Another important factor in a chemical reaction is the selectivity. Here we can see that the synthesis of gas COH2 product obtained over the various metal depends on the mode of CO chemistry option. Here we can see the CO and H2 will combine when copper, silver, and gold as an catalyst used over here. We get the methanol synthesis, and when we use the nickel, it's with the methanations and hydrocarbons. By the Fischer-Tropsch method, we are able to find out when cobalt, iron, and the ruthenium has been used as a catalyst. Selectivity is always important factor. Hydrogenation reaction, the chemoselectivity has to be achieved. Hydroformylation, regioselectivity have to be achieved. Hydrogenation reactions, diastereoselectivity selectivity and enantiomer selectivity has been achieved. And why it is important, the selectivity, we will just take one example and then we'll go ahead. Why did this thing has happened? Anybody knows about this? The thing has happened because of the 1950s, a German company, Chemie Grunthal, developed a thalidomide, which was a market in Europe for morning sickness in a pregnant woman. But the thalidomide was far from the safe. It was not that safe. The first known victim of thalidomide was a girl born with no ears on a Christmas day of 1956. Ironically, the daughter was found to be the Grothanol's employee. In time, the thousands of children around the world whose mother took the drug while pregnant were born with a severe physical disabilities, including flipper-like arms and legs. So the thing has happened. The R-thalidomide is found to be a sleeping-inducing drug, and the S-thalidomide is tetragonic. The thing has happened. The racemization happened in the body, and because of the racemization that happened in the body, the things has happened over there, and the children were born with the disabilities. In September 1960, Dr. Francis Oldham Kelsey, a young pharmacologist of FDA, was asked to review the drug. Because of the Dr. Kelsey perseverance, the drug never received the FDA approval, and in 1962, it's banned worldwide. Reason for the catastrophe is R-thalidomide is selective, while S-thalidomide is tetragonic in effect. When it came to scaling up the manufacturing, not only into the body, but in the manufacturing process also, less care was taken in manufacturing the only enantiomer, and the drug ended up into a shelf as a racemic mixture that has been taken, and then the effect has observed. This is the case what we are able to see, the mirror image RNS enantiomers. This is the oxidation of alcohols by its selectivity issues. That's why the example has taken from cinnamol alcohol. We can reach up to the benzaldehyde. We can come to the propanol, then propane, and styrene and thiolbenzene. The selectivity, what exactly you want to prepare, that will take care of the catalyst. Oxidation of aromatic alcohols to carbonyls. So the aromatic alcohols, another route of oxidations of the carbonyl by the metal oxides. The catalyst system works with the selectivity as a goal in this conversion. So we may be able to see, we are able to see the oxygen on oxygen over here. If we use a metal oxide, and selectively we are able to find out the carbonylations properly. So the conventional synthesis of the Friedel crafts, just for the example, reaction using homogeneous Lewis acid or strong proteinic acid, electrophilic aromatic substitutions named after the Charles Friedel and James Scarf. The drawback was the harsh reaction conditions, stoichiometric amounts of catalysis, then generation of a large volumes of corrosive and toxic waste. So this Freund-Kraft reactions, the acylation reaction, what we are able to see. This is the reaction what we have got where we are from alcohols, aromatic alcohols, we are able to get an aldehydes. NMN2 acts as one of the major over here, and at time requires 2.5, and the 100% conversion we are able to get. Initial rates of the hydrogen peroxide decomposition has been studied over this catalyst of manganese oxide, manganese dioxide, and then what we are able to find that the BET surface area is very high for the NMN2, and initial rates is also high as compared to the other manganese dioxide catalyst. The catalyst hydrogen decomposition's BET surface area, which has been mentioned over here, +3 and +4 oxidation state, how it can varies in MnO2 and NMnO2 and MnO2. It has been labeled. So role of MnO3 in oxidations. So we can see that the alcohol or phenyl alcohol is there, the Mn active catalyst is there. Then we are able to find the Mn+3, Mn+3 combined with the vacancy, anion vacancy and oxygen to give us the Mn+4. So the Mn3 plus Mn+4, the role becomes very important over here to understand. The percentage of Mn+3, Mn+4 is variable, and in case of ANMnO2, we found that 84.20% of Mn+4 and 15.80% of the Mn+3. The thing is, what we are able to find out, we are able to find the bulk and the nanostructure. Rather than the bulk, the TBHP, when we are going from the alcohol to the carbonyl compounds, so what happens? If you use the bulk MnO2, the process is slow, but when we use the nanostructures, the process is fast. Mixed metal oxides and their advantages as in catalyst. Mixed metal oxide are oxygen-containing combinations of 2 or more metallic ions in proportion that may either vary to be defined by a strict stoichiometry, or from obtained in the form of a powder or a single crystal. So this is a perovskites what we are able to get, the mixed metal oxides. BaTiO3 is one of the example what I'm setting over here. Few minerals have experienced such a dramatic change in scientific attentions as a perovskite. More than 100 research papers in the first 50 years has come, and more than 3,000 publications are annually coming up. The mineral was discovered by the Persian mineralogist Gustav Rose in the Ural Mountains of Russia. This was sent to him by his Russian colleagues and notable mineralogist August Alexander Kammer. The perovskite minerals are named after a Napoleonic War veteran, Count Leaf R. Perovsky. The structure of the perovskite oxide was resolved only with advent of X-ray diffraction techniques about 50 years later. The first industrial patent of the perovskite research came only in the patent of US by Victor Motz Goldsmith. In 1940, the pressing military and industrial need of the ferroelectrics with a high dielectric constant led to discovery of BaTiO3 ceramics. Their catalytic efficiency was realized much after that. So it took a long time to realize the catalytic activity of BaTiO3. The A stands for the anions, the cations, those who are rare earth, alkaline earth, alkali, and large anions. Example, Pb, Pb+2, Bi+3, and fits the dodecahedral size of the framework. And the B ions to be 3D, 4D, or 5D transition metal elements like cobalt, nickel, copper, and O stands for oxygen. So this kind of a structure we are able to get AbO3. What makes the perovskites oxides versatile? Their ability to tolerate significant partial substitutions, variable oxidation state, oxygen non-stoichiometry. Perovskite as a catalyst, the catalytic activity depends on the nature of A and B ions and on their valence state. Catalytic activity generally determined by the B cation. Like we have got the B cations, they are aluminum, chromium, iron, gallium, indium, and scandium. These are the defining that how the catalytic activity will take place in case of the AbO3. The perovskites or the mixed metal oxides can be synthesized by co-precipitation, ceramic heating, sector precursor method, spray drying, freeze drying, or soldier method. This is one of the example what we have got the benzylic alcohol to carbonic. So the benzylic alcohol is getting converted to the carbonic, and we are using cerium, chromium oxide as a catalyst, which is a BO3 kind of an catalyst, mixed metal oxide. And the conventional route is we take an oxidant, and by taking the oxidant, we do this. The conventional metal says that the stoichiometric amount of the oxidant is required. Dichromate and permanganate produce a large amount of a solid waste, leading the environmental problems. Supported noble metals such as the palladium and gold, they are not cost effective. Homogeneous catalyst systems, there is no recovery of the catalyst. So we are moving towards the parts of the cerium chromium oxide, that is an AbO3 type of a mixed metal oxide. So average, when we calculate for the cerium, the amount of a cerium found to be 20.15, chromium is 19.85, and the remaining part was there for the oxygen. The bracketed amount of the calculations has been given the standard deviations, what we are able to find out. The conformation of the oxidation state, the chromium observed to be the binding unit of chromium observed to 576.3 electron volt, which matches with the chromium binding and chromium 2p binding energy 576.4 electron volt, which is in chromium oxide. So it is confirmed that the chromium is in plus 3 oxidation state in the cerium chromium oxide. The effect of temperature and solvent on oxidation of benzoyl has been studied, and is found to be that acetonitrile as being a good solvent to it. The 10 millimole of the catalyst is found to be good catalyst, good amount. The cerium chromium oxide, the catalyst loading. And there are some subset studies which has been carried out. The conversion has found to be 100%, and the selectivity is also found to be 100%. There are some oxidation of alcohols which has been studied over here. And finally, the research opportunities what we are able to get. The studies of the catalytic reaction mechanism, chemistry of surfaces, application of the quantum chemical methods in catalytic research, novel catalyst supports and adsorbent, new catalyst and catalytic processes for environmental protections, new catalyst and catalytic processes for petrochemistry, oil, processing industry, and organic synthesis, new catalyst and catalytic process for nitrogen chemistry, catalytic deactivations, homogeneous catalysis and catalysis by complex compounds, catalysis in green solvents. Finally, I would like to thank the principal of our college, Dr. C.S. Sponsi, for allowing me for being a part of this conference, head Dr. A.R. Anthony, Professor Radha Jairam, with whom I carried out my doctoral work, Professor S.D. Samant, the head then that time, Sovian and Kirti, for having the patience and following me up regularly, and Akanda is my mother and father. Because of them, I'm present in front of you. Thank you. Thanks a lot.